Hi everyone, welcome to Quantum Club Colloque de Physique tonight. So I'm Elliot, I'm the president of the Quantum Club, and so we are a student association where we organize a lot of talks about quantum, of course. And so tonight we're happy to collaborate with the Colloque de Physique, so invited Erez Berg. In 2 weeks we will have a talk of Boris Koch, same hour, same room. And in 4 weeks it will be Alberto Morpurgo. And we have kind of a tradition, so before every talks of Quantum Club we first start with a warm-up talk. And tonight we listen Michael, and just before Anna will say a few words, and then we will start. Thank you very much.
Okay. So I would like to say a few words about our today's speaker, and we invited Erez as a main speaker today, and Erez did his PhD in Stanford first, then postdoc in Harvard, and now he's a full professor at the Weizmann Institute of Science. And I guess the main research topic is in condensed matter theory, in between high temperature superconductivity and topologies from electron correlations. And I guess today we are going to talk about strange metals and how they can be influenced by superconducting puddles. And before that, we are going to have a brief intro to Fermi liquid theory and some ARPES results from the Michael, as Elliot said, from ARPES group. And Michael, now the floor is yours. Thank you very much.
Well. Thank you all for coming. Thanks for inviting me. I start much more mundane than Erez with strange metals. I will start with completely normal metals, I would say. And how does this work? Good. Seems to work. And normal metals, well, I start really from the beginning. Principle, it's a potential which is filled up with electrons. They're fermions. They follow the Pauli exclusion principle. So you can imagine really layer by layer our Fermi seas getting filled up until we have no electrons anymore, and we reach the end of our Fermi sea, which is then called the Fermi edge or the Fermi energy. And in principle, this problem is completely untrackable. It's 10 to the 24 electrons all interacting with each other with Coulomb interaction, which is not a weak interaction, by the way. But as you might have guessed already, there's good theory to actually work with this. And probably the current running theory to describe this was developed by Landau, first to describe helium-3, which is the Fermi-Landau theory. And the idea works in the following way, that you start with a completely non-interacting Fermi sea. And in this Fermi sea, you can calculate everything. It's single particles, essentially. And if you now increase the interaction very slowly, say adiabatically, what you end up with is having the same ground state, but different properties. We renormalize various properties. In particular, we renormalize, for example, the mass, which then would renormalize the energy momentum dispersion. You can kind of imagine our fermions now being stressed with the interaction, which means we cannot talk about electrons anymore. Instead, we talk about quasi-particles. And all of the interaction kind of acts as if our quasi-particles carry a heavy weight with them, making it harder to move. And to understand how our Fermi liquid now behaves, we kind of look into the easiest excitation we can have, which is single particle excitations. And single particle excitation would be, for example, adding an electron to the Fermi sea with particular energy epsilon above. And the idea, first order idea, is we have to look at what electrons can it scatter with, which is actually not that many, because if it has an energy epsilon above the Fermi lake, it can actually only interact with a thin slice on the edge of the Fermi sea, thin slice with a width of epsilon. So if we assume constant density of states and everything, that's factor of epsilon. And also the available phase case to scatter into is, again, it needs to be above the Fermi sea. Whereas within the Fermi sea, every state is occupied. So we have 2 factors of epsilon. And our scattering rate is proportional to epsilon squared. We can follow similar arguments with the temperature. The temperature will smoothen out our Fermi edge by a factor of t, for small temperature at least. And then our Fermi sea is starting to be wavy, and we can have, in principle, interact with electrons above the Fermi level and also scatter into the Fermi sea where there is space. So again, this leads to a proportionality of t squared, and in total we have the probably by most of these people here well-known dependence of the scattering rate by epsilon squared plus t squared. Which means in transport, the resistance is directly proportional with the inverse of the lifetime, but also the scattering time then, to the t squared, and our stereotypical Fermi liquid of the day is going to be strontium ruthenate. In principle, it's a layered material, so we have different resistance in this layer than out of this layer. But what we can see if we measure the resistance is that the resistance really follows perfectly this t squared law for low temperature. You can see here the x-axis proportional to t squared here, and it's perfectly linear. Up to a point which is about 25 Kelvin, and then for warmer temperatures, the Fermi liquid theory breaks apart. But for cold temperatures, it's basically spot on. I'm not doing anything with transport. As Anna already told you, I'm doing ARPES here. I guess most of you know what is ARPES, but quick to remind you maybe, we use ultraviolet light to excite our quasi-particles in the metal. The energy of those quasi-particles is then high enough to escape the potential. Because of symmetry reasons, more or less, the momentum in plane is conserved. And if we measure now the angle of the executing electron and the energy, we end up with these nice dispersion bands of the quasi-particles within the metal. The experiment I'm going to show you was actually not performed by me, but Andrew Hunter, right in the lab, across the hall, about 50 meters in this direction. And to give you an idea of what to look out for, as you've seen, we see the dispersion of the quasi-particles with ARPES. So in particular, we see the mass of our quasi-particles with varying degrees of this curvature. In principle, this mass can also be negative, so we have a whole light band. And what we are quite interested in, if we take a single cut along a single momentum, we get the energy dispersion for our quasi-particle. And in particular, we look at the width of our energy dispersion, which should be Lorentzian. This is again proportional to our epsilon squared plus t squared, which we've seen from the Fermi-Landau theory. And for strontium ruthenate, you might have guessed it already, this works perfectly well at low temperatures. So I have the non-interacting bands as single lines here. You can see that the quasi-particle bands, they're a bit flatter than our non-interacting bands, meaning they have a higher mass. You can also see that at the Fermi edge, they're fairly sharp. And then if you go lower in energy, they get wider and wider. Let's move on from Fermi liquid theory. There's a quite famous experiment for strontium ruthenate with transport, where they took a sample, they strained it from both sides. So those two are anvils which press the sample in the middle, and they measure the resistance, temperature dependent. And at zero strain, which is here on the right side, quite obviously, we have our Fermi liquid. This is the plot of the exponent of this t dependence. So on the right side, we have again our t squared law. So if you move with higher and higher strains towards this value about, we see that even at cold temperatures, we change from our t squared law to about a t to the power of 1.5 law. And with ARPES, we kind of want to know what actually is going on at this point. So we somewhat repeated this experiment. We also have our crystal here, and we pressed from both sides, applied uniaxial strain. And what we saw is that we have this band in particular, which seems to move lower and lower until it crosses the Fermi level. And in this direction, it looks like a whole light band, but in the other direction, it's actually an electron-like band, meaning it's a saddle point which we have here. It's a Van Hove singularity to be precise, meaning we have a singularity in a density of states. And now let's check if this is actually also the same point which we have seen in transport. So we looked at the energy dispersion, this small window and each momentum. We fitted the Lorentzian. Our Lorentzian now has a width depending on energy with the following function. And in particular, for this train, where we saw the Van Hove singularity crossing the Fermi level, we see the dip in the exponent similar to what the transport measurements saw. And with this, I'm already coming to an end. We now have an idea of how metals should in principle behave. We also saw ARPES as a bit of a probe for, first of all, Fermi liquid theory, but also for when it deviates from this Fermi liquid theory. And finally, we saw that if you move beyond Fermi liquid theory, we get to strange metals, to strange behaviors. And I think this is also a perfect transition to Erez, who will now explain you what the strange behavior is actually. Thank you all for your attention. Do we continue directly or?
Yeah, so first I'd like to thank Anna and Andrea for the kind invitation to visit here. Visit before a few years ago. It's always fun to be back. Second, I want to say please interrupt me at any point. I'd like to have this more as a conversation. And also thanks to Michael, who introduced the subject so nicely, and it really would merge very well into what I wanted to say. So I'd like to start by defining what I mean when I talk about this strange metal. Okay, so I think it's really important in this field. People use the term to describe somewhat different phenomena. So I think it's really important to specify what we mean. I'm a theorist, so I'd like to introduce a theoretical strategy to treat these problems, a view from some kind of large n limit, which allows us to access non-perturbative results may or may not be applicable to specific materials. And finally, I'd like to share some of our recent ideas about how a strange metal behavior, in particular in cuprate high-temperature superconductors, may be related to the presence of small superconducting puddles in the normal state. This is very much work in progress. Okay, we have one preprint, but I'd really love to hear feedback about it. We are very sure that the theory statements are correct. Whether that's actually the theory of the strange metal in cuprates, we're not sure. It's theory, not the theory of strange metals. Okay, so that's this talk. Okay, so before we talk about strange metals, let me briefly reiterate what Michael said about what are conventional metals. Okay, so one of the most successful theories we have in condensed matter physics is Fermi's Fermi liquid theory. Okay, and the idea, as was explained, we have electrons moving in a periodic potential and interacting with each other. This interaction is not weak, right, by any means. Usually it's very strong. Nevertheless, the astonishing fact is that we can treat excitations close to the Fermi surface at very low energies as if they were non-interacting particles with a modified dispersion. Okay, this is the Boolean zone, and this surface is the Fermi surface. So the low energy excitations of the system are described in terms of almost independent particles, quasi-particles, with modified parameters. Okay, with a new effective mass. These things live for a finite amount of time. They're not actual eigenstates of the Hamiltonian, but as you approach the Fermi surface, as you go to lower and lower energies, they become better and better approximate eigenstates of the Hamiltonian. Okay, and the statement is, if the system was perfectly clean, which it isn't in real life, but sometimes these systems could be very clean, and if the temperature goes to 0 and the energy of our excitation goes to 0, asymptotically, we actually have an exact excitation of the system described essentially by injecting or removing a single electron, or at least injecting and removing a single electron has a finite overlap called the quasi-particle weight with the exact excitation of the system. Again, from that very simple idea, you can actually calculate a lot of things, okay? You can calculate any property, any low energy property of the system that you like. In particular, you can calculate transport at low, which is dominated by these low energy excitations. You can calculate magnetic susceptibility, you can calculate specific heat, and so on. Okay, so just from this very simple picture, you don't necessarily know easily how to calculate the effective mass, for instance, or other effective properties of the low energy excitations, but you can fit these properties from experiments, and once you have that, you can calculate anything you want.
May I ask you to restart the sharing slides, because in the Zoom slides they are not changed.
Yeah. So I just stop the share and restart it. Yeah. So, share.
Okay, thank you very much.
Is it they did not? Okay. All right. So so in particular, so here's the resistivity of a conventional metal. This is copper as a function of temperature over a very wide temperature range. Okay, and you can understand this curve from Fermi liquid theory plus Boltzmann transport theory in great detail. Okay, so you see here different behavior at high temperature and at low temperature, and just by fitting a few experimental parameters, you can understand this curve. Okay, so the fit is fit to Boltzmann theory. Okay, so what's going on here is that the electrical current is carried by these quasi-particles. The mechanism that limits the resistivity is scattering of the quasi-particles off phonons, which are basically vibrations of the crystal lattice. At high temperature, this scattering rate of quasi-particles off phonons is linear in temperature. At low temperature, which is below some fraction of the characteristic energy of the phonons, that crosses over to t to the fifth power. At very low temperature, the dominant scattering mechanism is expected to be electron-electron scattering. That's extremely weak in copper. Okay, that's not observable actually in copper. In other materials, it is. Okay, but we can understand the crossover between all these different regimes using this theory. Okay, so that's a conventional metal. So what's a strange metal? Strange metal is basically a metallic system which falls outside of this paradigm of condensed matter physics. Okay, so we have a metallic system whose properties we cannot explain using the conventional theory, okay, Fermi liquid plus Boltzmann theory, in the limit t goes to 0. Okay, so remember, Fermi liquid theory is an effective low energy theory. So if we want to be able to make sharp statements about whether something it behaves like a Fermi liquid or not, we should always, at least in principle, take the limit of asymptotically low energies. Of course, in practice, that means go to the lowest available temperature and find a behavior which cannot be described within Fermi liquid theory. And now, why is that interesting? Of course, this is rare. Most of the metals we know are Fermi liquids. Why is this interesting? Well, first of all, there are materials that seems to fall outside of the behavior we read in the textbooks, and the question is what's going on. Okay, so one reason these things are interesting is because we don't understand them basically, and the second reason why strange metallic behavior is interesting is because it often comes together with other interesting phenomena like unconventional superconductivity, for instance. Very often what people find is that unconventional superconductors emerge out of a normal non-superconducting state that has this characteristic, okay, which is a strange metal. So these things seem to go hand in hand pretty often. The long-standing idea was, well, to understand unconventional superconductivity, for instance, we first have to understand the normal, the non-superconducting state out of which the superconductor emerges. Okay, so how do you know that something is a non-Fermi liquid? Well, we know exactly how a Fermi liquid should look like. So we just find a behavior that seems to violate that expected behavior. The most common diagnostic, just because it's the first thing that you would measure experimentally, is the temperature dependence of the resistivity. Okay? What people often observe, which is sort of the first signature of a strange metal, would be an anomalous temperature dependence of the resistivity, of the electrical resistivity at low temperature. Okay, there's always some constant, which is the T goes to 0 limit of the resistivity, typically due to impurity scattering. But if you look at the first temperature dependent correction to that, that might follow a power law dependence, T to the power alpha. Okay, a Fermi liquid theory tells you that alpha should be 2. So the temperature dependence of the resistivity should be T squared. We'll go more into that in the next couple of slides. But anything which is less than 2 is a strong violation of the Fermi liquid theory. People often, in different systems, people often, but not universally, find that alpha is equal to 1, namely the resistivity is linear in temperature. Okay, so here are some examples. This is a cuprate superconductor at various degrees of doping. Okay, and you see this, especially at this value of the doping, you see this beautiful linear in temperature resistivity that extends strikingly down to the lowest temperatures that you can measure. Okay, so this experiment was done in the presence of a high magnetic field that suppresses superconductivity. Okay, without the field, the sample would actually be superconducting. But you suppress the superconductivity by a field, and this linear dependence of the resistivity extends down to the lowest temperature that people have measured, okay, below 1 Kelvin. Okay, and here's another topical example. Okay, this is magic angle twisted bilayer graphene, and the experiment finds that over a wide range of electron density in the system, the resistivity actually follows this linear in T law. Okay, sometimes down to strikingly low temperature. This is tens of millikelvin in this system. Okay, so again, why is that interesting? As simple as it sounds, so linear in T resistivity, there's no good theory of that. Okay, so this is not something you'll find in condensed matter textbooks. Okay, now and the two things to remember here. Okay, first of all, getting linear in T resistivity down to low temperature theoretically is hard, and I'll go into why that's hard. Okay, but as a theory problem, we really don't know of a good mechanism that can allow this to persist down to very low temperature. Okay, the other thing to bear in mind about this is that just having linear in T resistance over some temperature window is really nothing special. Okay, so as we saw, copper has a very wide range of temperatures where the resistivity is linear as a function of temperature, but that gets cut off. It's below some temperature of a few tens of Kelvin. Okay, the really special thing is the limit T goes to 0. Okay, that really tells you something about the nature of the quantum ground state of the system. And to be able to sustain this behavior all the way down to the lowest temperatures, the ground state has to be fundamentally different from a Fermi liquid. Okay, so that's why we want to really be able to make a sharp distinction. We really want to insist on this condition. Okay, so to discuss why, at least what are the essential ingredients that we know must be there in order to violate Fermi liquid theory, let's go a little bit into the origin of this T squared or energy squared law for the scattering rate of a quasi-particle close to a Fermi liquid. Okay, so where does this law come from? Probably many of you have seen in classes in condensed matter. It really comes from phase space of these low energy excitations close to the Fermi surface. Okay, so if you look at the density of states of quasi-particle excitations close to the Fermi surface, that's a constant. Okay, there's a constant density of states. The value of that density of states depends on the shape and the shape of the Fermi surface and the effective mass and so on. But there's some constant. And now if we start from a single quasi-particle, some energy epsilon above the Fermi surface, and ask about the collision rate or the scattering rate of that electron with all the other electrons, a simple phase space argument would give you immediately that that actually goes like the energy squared. Okay, so that a quasi-particle can scatter off another quasi-particle close to the Fermi energy. So this one might scatter to here to conserve momentum. There's some field state that would have to scatter to an empty state over here. Okay, the initial quasi-particle would lose some amount of energy. The scattered particle would gain the same amount of energy. Okay, and you have to integrate both over this energy transfer and over the initial energy of the scattered particle. Two integrals over energy would give you epsilon squared. Okay, so it's as simple as that. That's actually the argument. Okay, and as mentioned by Michael, this is sort of a leading order calculation. But the beauty of Fermi liquids theory is that that actually extends all the way to intermediate and even strong coupling. Okay, so the coefficient of this T squared and epsilon squared term is hard to calculate, but the power law is very robust. And that really is one of the telltale signatures of a Fermi liquid. Now, of course, let me stress, just seeing T squared or epsilon squared does not mean that this is the right picture, that it's a Fermi liquid, that this is the right mechanism, and so on. Okay, there are actually mysterious puzzles in condensed matter where we see this T squared and epsilon squared behavior where we don't expect them. But any violation of this law means that something about this simple phase space argument has to break down. Okay. So how do we get a deviation from this T squared and epsilon squared behavior? Well, one thing is for sure, we must have a pileup of low energy excitations of the system close to the Fermi energy. Yeah, there's a question?
I mean, that's the question. Your argument is totally correct for tau, but what you measure in transport is not directly tau. You need to invoke unklappen,
yes.
momentum.
Absolutely.
And there'll be some caveat there that,
Absolutely, yeah. So, right, so very good point. Okay, so this is a little bit of a cheat. What I'm describing is the lifetime of a single quasi-particle. What's measured in this can be measured directly in ARPES experiment, but if we think about transport, that's not enough. Okay, so transport is really measuring the rate in which the electrical current, which is a collective phenomenon of all the electrons, is decaying, not just a single quasi-particle. Okay, and to have this T squared dependence of the single quasi-particle scattering rate appear in the resistivity, we must have some mechanism to relax the total current or the total momentum of the electrons. In this sort of example of Fermi surface, that would come through umklapp scattering. Okay, you can scatter into the next Brillouin zone, which really means that the total momentum is not conserved. Now, so could there be a caveat to the argument there? Typically, there wouldn't be. So typically, you would say, well, the relaxation time of the current, if anything, could be much longer than that of a single quasi-particle. Okay, so meaning the scattering rate of the current can be much smaller than that of a single quasi-particle. For instance, if we didn't have umklapp scattering, we can still relax single particles, but not the total momentum of the system. So we don't expect quasi-particles to live longer than the current. We don't expect quasi-particles to live right. So if anything, they live shorter. Okay, so it's an upper bound. Okay, other questions? All right. So yeah, so what we're really after when if we want to explain strange metal behavior, assuming that at least this Fermi liquid picture is not a completely wrong starting point, meaning we still have a Fermi surface, we still have almost well-defined quasi-particles that scatter off something, is that we need to explain the source of this anomalously strong scattering, which means that there needs to be an unusually high density of low-energy excitations in the system that would provide a parametrically faster scattering mechanism for the electrons. Okay, so we saw that in a Fermi liquid, the excitation of excitations that scatter are the same electrons, and they have a constant density of states at low energy. Okay, and it's really scattering of an electron off a quasi-particle, quasi-hole pair. To get something different, we'll have to have a much higher density of states at low energy. Okay, and we already saw an example of where this high density of states at low energy might come from. Okay, so suppose we somehow tune our Fermi surface, tune our system such that the Fermi surface is exactly at this point of topological transition between one connectivity of the Fermi surface and another one. Okay, so this is a saddle point in terms of the dispersion, epsilon versus k. It would look like this. And specifically in two spatial dimensions, it turns out that if you calculate the total density of states, that actually has a logarithmic singularity exactly when the Fermi level is at this saddle point. Okay, and that means that there are much more electron hole pairs that are available to scatter our quasi-particle if the system is tuned to the vicinity of this point. Okay, and here actually this point that was mentioned before comes in a very important way. Okay, if you calculate the scattering rate of a single electron close to the Fermi surface, as opposed to the scattering rate of the electrical current, you'll actually get parametrically different results in this example. Okay, so the electrical resistivity turns out to be t squared times this logarithmic correction, log of the bandwidth basically divided by temperature. If you calculate the scattering rate of a single electron, that actually follows a power law. That's t to the power 3/2. Okay, so it's a non-Fermi liquid power law, which doesn't show up in the resistivity. Okay, so there is a violation of the t squared law, but it's not by power law, it's only by log. Okay, and can this be actually done? Okay, so the ideal experiment would be to take a metal which we can somehow tune between, we can somehow deform controllably the Fermi surface between this situation and that situation. Okay, and yes.
Actually, maybe following up on what Alberto asked, this t squared log t, does that include the Unclass scattering, or is just plugging in the?
Yeah, no. So to really see this in the resistivity, you must have Unclass scattering. Okay, so this is by the way, the scattering process that I illustrated here is an Unclass process. Okay, but this comes from processes that may be Unclass or non-Unclass. There must be Unclass somewhere. Okay, but the important thing is that it comes from two electron scattering processes where one of the four states involved, either initial or final states, is right at the Van Hove singularity. Okay, and it turns out that this picture is still a little bit misleading. You actually also need multiple bands to see this extending down to the lowest temperatures. Okay, that has to do with the kinematics, with the particular kinematics of when the scattering process is available. Okay, but luckily in the example that I'll show, all of these conditions are met. Okay, so you can have Unclass scattering, you have multiple bands, and yeah. So luckily, as Michael showed, we do actually have an example where we can do exactly this. Okay, and this is really the example that got me actually thinking about this problem. This is a strontium ruthenate, where by applying strain, you can really control the Fermi surface of the system and tune it to be basically sweep the Fermi surface across this topological transition of the Fermi surface. Okay, and this was first demonstrated by Clifford Hicks et al. Okay, that you can really so this is a DFT calculation. He did an experiment that was shown by Michael, that I'll show in the next slide. Okay, but nowadays you can really image using ARPES this thing. Okay, so you do ARPES on a Felix and Anna's group do an ARPES experiment on a strain sample, and different parts of the sample have a different strain. So by imaging the band structure as a function of position, you can really see this topological transition occurring. Okay, so and this is occurring as a function of strain. Okay, when you apply uniaxial strain, the Fermi surface deforms. This is what it looks like, zero strain. And as you apply strain, one of the three Fermi sheets in the system, called the gamma band, is actually deforming most strongly. And it touches, this piece of the Fermi surface is approaching the brittle zone edge, touching its mirror image from the other side, and reconnecting in this way. Okay, so the idea is, if you look at the density of states of this gamma Fermi sheet, it's undergoing this Van Hove singularity. Okay, and the other really favorable thing about the system is that this is, of course, it's a 3D crystal, but the system is made out of extremely weakly coupled layers. Okay, so the system is very quasi two-dimensional. The coupling between these layers is very weak, and that means that this Van Hove singularity really behaved like a two-dimensional Van Hove singularity, meaning that we get this beautiful log divergence of the density of states, which is cut off only at a very low energy associated with the interplane coupling. Okay, so all of these conditions are met. What should we see for the resistivity that was shown by Michael? Okay, so this is a plot of the log derivative of the resistivity. So it's like showing a strain and temperature dependent exponent of the temperature dependence of the resistivity. And this value of the strain is where we expect the Van Hove singularity to occur. And we actually know what occurs there from the ARPES experiment. Okay, so you see this characteristic behavior on either side of this special point. You see blue. Blue is an exponent which is 2 or higher. Okay, but you see this fan shape regime where the exponent seems to deviate very strongly from 2. Okay, it's closer to 1.5. And just seeing this behavior is what you associate with a quantum critical point. Okay, so that means that you vary some non-thermal parameter in the system, and at zero temperature, there's some transition of between two qualitatively different states in the system. In the system, we know that there's nothing exotic going on. There is a quantum critical point, but a very boring one. It's just a change in the connectivity of the Fermi surface, and that's sufficient to give us this fan-shaped behavior. Okay, and you can look at the behavior of the resistivity as a function of temperature exactly at this point, okay, exactly at the critical value of the strain. And indeed, it can be fit to an exponent of 1.5, but it turns out that it can be fit equally well to t squared log t. And since this experiment, experiments at lower temperature have been done, okay, so the limiting factor, by the way, the reason this experiment was terminated at 3 to 4 Kelvin is because the system is going superconducting at that temperature. Interestingly, the superconducting TC is actually very dramatically enhanced when you approach this critical strain. Okay, but by applying a small amount of field, you can suppress TC and actually extend this measurement down to lower temperatures. And it turns out that as you do that, it looks like t squared log t is fitting the data a little bit better than t to the power 1.5. So we believe we understand actually the mechanism of the strange metal here. It's not that strange. Okay, it's just a log deviation from the Fermi liquid behavior, and it's coming from this pileup of a low energy density of states in close to a 2D Van Hove singularity. Okay, so a few lessons here. Okay, strange metal behavior doesn't have to be that to have a strange origin. Okay, nothing but a Van Hove singularity. The presence of this high density of states that gives rise to the strange metal can also make the system unstable to another kind of order. In this example, superconductivity, which is very strongly enhanced close to this point. Okay, but I like this example. I think this is one of the examples where we actually can understand.
Can I ask a question?
Yeah.
So, if we look at this from a different perspective, like Boltzmann transport.
Yes.
Whenever I have a energy-dependent density of states,
Yes.
I'm gonna get through Boltzmann
Yes.
something that is different from
Yeah.
a t squared with some
Yeah,
correction.
yeah.
So could this be a viable way to look at cuprates and
Yeah,
systems that are
I'm gonna get into that.
multi-band?
Yeah, I'm going to get into that soon. Okay, the next. Yeah, indeed, this is all what's going on here. Okay, so typically you'll get if you have energy dependent density of states, which you always do, you won't see a pure t squared. As long as the density of states at zero energy is constant, you'll see asymptotically t squared, very low energy, unless you have some singular density of states like you do here, but nothing more exotic than that. This can be perfectly described using Boltzmann transport. Okay, so, but you can ask, suppose I want to explain a power law behavior, which is with an exponent which is smaller than 1. In particular, I want to explain linear in T resistivity. Okay, which is very different from this thing. What kind of energy-dependent density of states do I need to get that? Okay, so that's not a hard exercise. Okay, using basically the same reasoning. Okay, so what profile of energy-dependent density of states do you need in order to get linear in T resistivity? Okay, so it turns out that what you need is basically a delta function in the density of states. Okay, so if you run the same argument. You say I have a background of a constant density of states. Suppose I have a dispersive band, but I also have a flat band, very close to the Fermi energy, or actually, let's put it exactly at the Fermi energy. And you do the phase space argument for this case, and you find that the scattering rate of electrons from the dispersive band, basically one electron from the dispersive band and one electron in the flat band, the phase space for that scattering event is linear in energy or linear in temperature.
Sorry, flat on a scale of kT, or?
Yeah, it has to be flat on the scale of kT, and its distance to the Fermi level has to be smaller than temperature. Yes. Okay, so this is what you need. This is not very easy to obtain. Unlike just having a 2D Van Hove singularity, at the Fermi level, which in a 2D system, whenever you tune some parameter, you'll inevitably get. Here you have to have this perfectly flat band, which is not a very natural or easy thing to get. It needs to be, as was mentioned, flat on the scale of kT, which means that if you go to lower temperatures than the bandwidth of this flat band, the linear in temperature regime behavior would be modified. And flat bands, just like Van Hove singularities, but in a more extreme way, tend to become unstable. So the system doesn't like to have a large degeneracy. Okay, quantum mechanics doesn't like a large degeneracy close to the Fermi level. So the interactions would tend to destabilize the system at low energies.
But why do you see this scenario as so exotic? If I have a multi-orbital system where with some strong hybridization driven by a crystal field, with energy scales of the order of kT,
yeah.
I will have something that looks like a flat band plus some itinerant band.
Yeah. So it's not so unusual to get this behavior over a range of temperatures, I think. So in fact, we propose this as an explanation for the linear in T resistivity in a different ruthenate, in the bilayer ruthenate, where there's a critical magnetic field, where the resistivity is linear down to quite low temperature. And there is a region of the band structure which is very flat, close to the band edge. The trouble is that it turns out that quite fundamentally, this behavior actually cannot extend down to the lowest temperatures. If you just assume this sort of weakly interacting model and calculate the entropy of the system, it has a finite offset. Okay, so this is not really if this would extend all the way down to the lowest temperatures, it would violate the third law of thermodynamics. Okay, so there's a lot of entropy coming from this flat band. So this has to be removed at some temperature. This cannot really be a theory for linear T resistivity that extends all the way to T equals 0. Okay, which doesn't mean that it can't explain, some crossover regime which looks linear down to quite low temperature if this band happens to be flat enough. Okay, so right. How much time do I have?
I guess 10 more minutes.
Yeah, 10 more minutes. So yeah, so let me actually skip a little bit. Yeah, I want to. Okay. This I do want to say.
We can give more.
Right. So
You can do more than 10.
It's late, and you guys, I don't keep you guys too long. A very recurring theme in the study of strange metals, and conceptually a very natural way to get a breakdown of Fermi liquid theory, starting from a Fermi liquid, is to tune the system to some kind of quantum critical point. Okay, we saw a very trivial form of a quantum critical point, namely a Lifshitz transition or Van Hoff singularity. There are much more interesting kinds of quantum critical points. For instance, we can tune a Fermi liquid to a point where the system is just on the verge of breaking some symmetry spontaneously, developing some kind of magnetic order or charge order. And when you do that, you'll get a pileup of low energy excitations, which are the collective fluctuations of the incipient order parameter of the system. Okay, another example is in heavy fermion systems, the system is just on the verge of undergoing a transition between a large Fermi surface and a small Fermi surface. Something special has to occur exactly at the border between the two. Okay, and it turns out that, again, in many cases, not universally, but you find that exactly at the transition point, you have a linear in T resistivity that extends all the way down to the lowest temperatures. When you tune your parameter, and in both of these materials, the parameter the non-thermal parameter you tune is magnetic field. Okay, so you have, this is once again, this alpha is the log derivative of the resistivity as a function of temperature, and it crosses over from being a Fermi liquid like to T squared on both sides of the critical point, but then it tends towards 1 exactly at the critical field, and there's this fan-shaped form, okay, which basically sharpens to a point towards 0 temperature. Okay, so this is qualitatively, this is what you expect if there's a quantum critical point. Okay, so at T equals 0, the system is either Fermi liquid on both sides or something else exactly at one point, at the quantum critical point. And as you raise temperature, the distinction sort of blurs and you get this fan-shaped behavior. Okay, so it's a very natural way to think about the breakdown of a Fermi liquid. Unfortunately, we don't actually have a good theory specifically for linear resistivity at the quantum critical point. Okay, it's an old topic. There's a lot of work on it, but unfortunately, it's still an open topic, or fortunately, depending on your point of view. Okay, so but that's not what I want to talk about. Okay, I want to talk about something else, and let me skip a bit. Oops. Yeah. Skip this. Okay, yeah, so I want to talk about a way to get a strange metal with a linear T resistivity, not at the quantum critical point, which is an isolated point at 0 temperature, but over an entire range of parameters. This work was done with my two brilliant students, Noga and Egatal, at the Weizmann Institute, and we collaborated very closely with Jörg Schmallian from Karlsruhe and Steve Kivelson from Stanford. Okay, so here's the plot of the log derivative of the resistivity as a function of temperature and doping in a whole doped cuprate material. Okay, so this is one of the cuprate superconductors. This behavior repeats itself, at least qualitatively, in many superconducting cuprates. Okay, so you see the same kind of fan-shaped behavior, okay, with an exponent which is close to 1. This is linear in T resistivity. But interestingly, you see that this fan is actually not confined to a point. Okay, so this lower dashed line is DC. Okay, you can suppress a superconductivity by applying a very high magnetic field. Okay, you need an extremely high magnetic field, tens of Tesla, because DC is so high. But if you do that, you reveal a normal state at very low temperature, where the resistivity actually continues to be linear down to the lowest accessible temperatures over an entire range of parameters, not just at the point. Okay, so whatever is going on here in the normal state of the cuprate superconductor is not the quantum critical point for sure. It looks more like, if anything, it looks like a quantum critical phase. Okay, there's an entire 0 temperature phase, if you extrapolate, that seems to be a non-Fermi liquid. Okay, it violates the behavior that's expected for a Fermi liquid. And the other thing to note here was noted already a while ago by Nigel Hussey and collaborators, that this linear in T behavior seems to terminate not too far from where superconductivity actually disappears. Okay, so the end of the superconducting dome is right here. There's a superconductor to metal transition, and at a slightly higher doping, also this red color starts to cross over towards blue, which is 2, which is Fermi liquid behavior. Okay, so we believe that somewhere far away, far out enough in doping, the system crosses over eventually to being a more or less conventional Fermi liquid. But in the same place where the 0 field ground state is a superconductor, also the normal state is this strange metal with linear resistivity. Yes.
Can you just share again the screen, because now
right.
it's sharing.
Yes. Share.
And what is the magnetic field here?
Yeah, so the magnetic field varies. So if you're out here, you don't need a large magnetic field to suppress DC. Okay, if you're here, you need a much higher magnetic field. So just because DC is higher. Okay, so the field varies between a few Tesla and a few tens of Tesla, like 30, 40 Tesla. Okay.
For each point here on this diagram is different.
Sorry?
For each point on this diagram is different.
Yeah, so each point is actually, what's actually measured is the resistivity as a function of both temperature and field for every point. Okay, and if you measure at 0 field, it would look like this, which just drop to 0. You measure at higher field, it would extend to lower temperature and then drop to 0. Okay, but if you want to measure all the way down to the lowest temperature, you'll need to some threshold field, and that varies. And it's a good question. The resistivity in the normal state is a little bit field dependent. Okay, but let's just think about this as the resistivity as a function of temperature and doping at 30 Tesla. Okay, it's some fixed field. It might look like this. Okay, and moreover, what I want to imagine is that the main effect of the field is just to suppress superconductivity. Okay, so we imagine that if we could somehow magically suppress superconductivity without applying a field, we would see a metal whose resistivity is described by this plot. Okay, that's not Of course, not quite the case. The field is also doing other things, but we imagine that this is the main effect. Okay. All right, and let me also mention that this type of behavior of linear T-resistivity that gets revealed when you suppress an unconventional superconductor is actually not special to the cuprates. Okay, that's actually seen in other materials. Okay, so this is a compilation of data from different cuprates. Okay, what's plotted here is the coefficient of the linear T-resistivity as a function of doping, and TC as a function of doping for different materials. Okay, and you see that in this review article by Louis Taillefer, you see that there seems to be a correlation between where this A coefficient vanishes and where TC vanishes. And moreover, here's similar behavior in an organic superconductor, which is also an unconventional superconductor, okay, believed to be D-wave. But other than that, completely different material, and you see also similar behavior. Okay, so here, the control parameter is not doping, it's pressure. You have a superconducting dome-like shape, and you have a linear T-resistivity in the normal state. It looks like a combination of T plus T squared, and the coefficient of the linear T term disappears close to the critical pressure, where also superconductivity disappears. Okay, so what is going on? Okay, so there are sort of two ways to interpret this behavior. Okay, one way to interpret it is to say, well, there's something that causes superconductivity at zero field, and the same thing is also causing linear T scattering of the electrons at in the normal state. And there's another way to interpret this diagram, which is to invert the causality and to say, well, it's somehow the remnants of the superconductivity that exist even if we suppress global superconductivity that are causing the linear T scattering in the normal state. Okay, and we want to take the second point of view. Okay, we want to focus on this extended low temperature regime of linear T resistivity, and we want to interpret it as a remnants of superconductivity that survives even beyond the point where superconductivity globally is destroyed and are causing this linear T scattering. Okay, now it turns out there's plenty of evidence that even in the normal state, superconductivity is not completely destroyed at a local scale. Okay, this has been known for a while. This is these are STM experiments by Yazdani's group from a while ago, and more recently by Millen Allen's group. Okay, and what they see is that okay, so this temperature for this particular sample is above TC, where basically the resistivity is already finite. But if you do STM, you see that the gap, the gap feature in the spectrum that you associate with superconductivity is not actually zero everywhere. Okay, so in this color map, white means no gap. That means constant density of states at the Fermi level, and these red patches are regions where locally the gap is finite. And you see these sort of little islands which seem to maintain their superconducting gap even above TC. The size of these regions is quite small. Okay, it's a few nanometers. So that's yeah. There's no scale here, unfortunately, but yeah, the size of this thing is 3-4 nanometers. And this is a similar plot from Millen Allen's group. Okay, so these are samples with different doping. Okay, and the color shows the magnitude of the gap. This sample is actually not superconducting, okay, but still there's a lot of local superconducting-like gaps. Now, there's a lot of other experimental evidence that in this overdoped regime, where linear T resistivity is observed, the superconducting state, you don't suppress superconductivity, okay, the ground state is a superconductor, but the superconductor is very inhomogeneous. So it's not that the entire sample has a uniform superfluid density and constant gap. There are actually regions that are superconducting that below TC become phase coherent globally. Okay, so there's evidence from that from the behavior of the superfluid density as a function of doping. It looks like there's a big fraction of the electrons in the overdosed side that are not participating in the superconductivity, okay, that are not condensed. And there's further evidence in optical conductivity and specific heat and so on. Okay, the theory of that, there's a nice theory by Doug Hiley and Steve Kivelson. The idea is that in an unconventional superconductor, in a non-S-wave superconductor, in the presence of disorder, superconductivity would be destroyed ultimately by disorder, but it would not be destroyed uniformly. Okay, there would be some regions where it would be destroyed much before other regions, and that's the origin of these superconducting puddles. Okay, so our idea is to think of the following. Suppose we suppressed superconductivity either by raising temperature or at low temperature by raising field. We destroyed the global phase coherence of the superconductor, but not the local pairing in these superconducting islands. And our conduction is now mostly carried by the normal part of the sample, by basically a normal metal. But electrons from this normal metal will scatter off these superconducting islands. In particular, they would Andreev scatter. And it's this Andreev scattering, in particular, inelastic Andreev scattering of the electrons, that's the source of the linear NT resistivity. Okay, so we'll go a little bit in more detail into that. Just take 5 minutes. Yeah, question? 5 minutes. Yeah. Okay, so very briefly. Okay, so we want to write some model that describes these puddles interacting with the electrons of the metal. We want to start in particular from a single puddle. Let's imagine that these puddles are very far apart, so we can sort of treat them one by one. And there's a simple Hamiltonian that you would write. Okay, we start from the puddle being completely isolated from the surrounding metal. Okay, suppose that to zero order electrons cannot go in and out. Then this puddle will have a well-defined charge, okay, some well-defined number of Cooper pairs, and it will have a phase. It will have a superconducting phase, and from quantum mechanics, we know that the phase and the number are actually conjugates. So if the number is very well-defined, the phase is very fluctuating, and vice versa. And there's some charging energy, okay? It's like a Cooper pairs in a box, so it costs some finite energy to charge the system, okay, to add or remove Cooper pairs. And moreover, because of the landscape of the disordered potential, this superconducting islands likes to have a certain charge. Okay, so there's some background charge that the system likes to have in the ground state, and this number doesn't have to be a integer. Okay, and the ground state of the system would be the closest integer, n is an integer number, the closest integer to this background potential, basically. Okay, so this is what the energy levels of an isolated dot or isolated island would look like. They're parabolic in n, and we have the two lowest energy levels of n naught and n naught plus 1 that are separated by this energy delta. Okay, so and now the coupling between the metallic electrons and this superconducting dot is described by this Andreev-like term. Okay, so we can have a pair of electrons jumping into the dot or jumping out. Okay, we can also have Coulomb interaction between the density between the number of Cooper pairs on the dot and our normal electrons. Okay, so that's the model. Pretty simple model. We can simplify it further. If we go to low enough energies, we can, and the superconducting puddle has a finite charging energy, we can actually project out all the energy levels of this island except for the two lowest energy levels, okay, that have n and n plus 1 electrons. Okay, and depending on this parameter delta that can vary between one puddle and the other, these two levels can be degenerate with each other. Okay, so suppose there's some distribution of this random parameter delta, we'll get a probability distribution for the splitting between the two lowest energy levels of this dot. Okay, so we can describe this island by a two-level system, basically focusing only on the two lowest energy levels. And we can write the same Hamiltonian just in terms of Pauli matrices, where this Pauli matrix sigma z, being +1 or -1, corresponds to the two lowest energy levels of our superconducting islands, corresponding to n and n+1 Cooper pairs. Okay, and yeah, this is redundant. You can ask, well, what's special actually about superconducting puddles? Okay, we can have two-level systems in a normal metal that have a completely non-superconducting origin, some kind of localized level that's interacting with electrons. We've actually studied a similar problem not for non-superconducting two-level systems and the scattering of electrons from these two-level systems. It turns out that these low energy excitations indeed can give you deviation from Fermi liquid. It's not linear in T, scattering rate in particular. It turns out that in this problem, you can get a resistivity exponent as a function of temperature, which is a continuous function of the microscopic parameters of the problem. It turns out that there's something very special about linear in T resistivity when it comes to superconducting puddles in particular. That was the interesting thing we found here. Okay, and finally, let me just end with this. Okay, I won't go into the details of the analysis of this model. Let me just say, why do you get linear in T from this problem? Okay, so there's actually a very, very simple argument. You just say, well, we have this parameter delta that controls the offset between the two lowest energy levels of our superconducting island. Okay, so suppose this parameter delta just has a uniform distribution. Okay, so in most of the puddles, we have a finite energy splitting between the ground state and the first excited state with n+1 Cooper pairs. But statistically, there would be a constant density of states for these puddles over a whole energy range, including 0. Okay, there's a finite probability to find puddles where the n and n+1 states are as close to 0 as you want. And now we have an electron from the metal that scatters off this puddle. Okay, and that scatters off this basically constant density of states. This is an inelastic Andreev process, meaning that the incoming electron is actually reflected as a whole, and adding one Cooper pair to the system, which costs a finite energy. Okay, and we have a constant density of states to have this process. Okay, and the phase space to do that is exactly the energy of the incoming electron. Okay, so this automatically gives you, in sort of a trivial way, it gives you linear in T resistivity. Okay, so there are subtleties that come in here. Okay, the first one is what actually guarantees that this density of states of low energy excitations of the islands is constant all the way down to low energy. It turns out that that's charge conservation. This is where the fact that it's actually superconducting islands, that these two levels, the ground state and the excited state of the two-level system, actually have a different charge. The other question is, down to what temperature would this behavior persist? It won't persist all the way down to 0 temperature. It would actually be cut off. What cuts it off, it turns out there are different mechanisms, but the one we think is ultimately dominant is basically Kondo effect. You think about the two-level system coupled to metallic electrons, that's a little bit like a spin impurity in a metal. And you know that there's the Kondo effect that the fluctuations of the two-level system eventually would be cut off by the Kondo effect. But we identified a parameter regime where that can happen, and only at an extremely, extremely low temperature. Okay, this is called the charge Kondo effect. It's not the spin Kondo effect. That our two levels are not spin up and spin down. They're n and n+1 Cooper pairs, but otherwise it's similar. Okay, so I probably just end here. Yeah, thank you very much.
Any questions?
So the STM data was for an overdoped cuprate?
Yes.
And the data from Nigel Hershey was underdoped?
Yeah, so,
Right.
right. The part of the data I was referring to was also overdoped. So it's, yeah, it's over here. Right? So,
Just to understand, what's the justification that the superconducting puddles are also in the hole-doped scenario?
Sorry, yeah, so let me clarify. So this is all hole-doped. Okay, so I'm actually not discussing electron-doped cuprates here. This is all hole-doped. What I mean by overdoped or underdoped, right? I mean, there's a maximum TC that occurs somewhere around 16%. Hole doping. Overdoped is basically beyond that.
Okay, so it's not a
there's underdoped, which is over here, which is actually not shown in this diagram. Still hole doped. Yeah.
Yeah. So if you have these puddles above the log TC,
yeah,
it's a bit strange because they're still superconducting.
Yes.
And for sure there will be some Josephson coupling, or maybe not for sure, but there may be some Josephson coupling.
Yeah.
Which would probably show up in the IV characteristics. So going to very, very low currents would start to see a better and better conductor.
Yes. Yeah.
Is that so, or?
Yeah. So right. So in this analysis, indeed, there's kind of there's one thing we ignored, which is right. I mean, we thought about scattering of the normal electrons off these puddles. But then we can also have a Josephson coupling between puddles, and eventually that's what would cause the system to go superconducting. Now, so what we assumed is that first of all, these we're far away enough from the superconducting to metal transition such that these couplings are weak. Okay, so basically, these puddles are far away enough compared to the thermal length or to the magnetic length, such that their coupling is very small compared to the typical charging energy, basically. In that regard, the Josephson coupling between the puddles would be a sublaning effect. Okay, so it would contribute something to the conductivity, but we assume that the conductivity is actually dominated by the normal electrons, not by Cooper pairs. Okay, that being said, there's one...
That is what you assume, that's not necessarily how it is, right?
No, absolutely. This is the assumption of this entire analysis. Okay, so this would only work if we're far away enough from the metal to superconductor transition where these Josephson couplings for sure are going to become important. Now, that being said, there is one experiment by Suchitra Sebastian where she goes to extremely low, so she applies a high magnetic field in YBCO and goes to extremely low current and sees that at extremely low current the system is actually superconducting. Okay, where previously people thought it's the normal state. Okay, so this comes very naturally from this kind of picture.
What about the D-wave order parameter?
Yeah. So the D-wave order parameter is very important to get these puddles in the first place in a good metal. Right? So you say, I take an S-wave superconductor and start adding disorder. When would disorder destroy superconductivity? It's basically on the verge of localization of the system. So it's when the system is so disordered that the normal metal is actually not a good metal anymore. Whereas in a D-wave superconductor, as we know, you'll start to destroy superconductivity already when the mean free path is of the order of the coherence length. Okay, so getting these puddles in a good metallic environment, you can only do that in a non-S-wave superconductor. Okay. Now the nature of the D-wave on every puddle, okay, that's a different question. I sort of ignored it in this analysis. And we can talk about that. That actually has interesting effects by its own.
Listening to your talk, one is also tempted to make an artificial system and make puddles on a metallic layer. But I suspect that there is a subtlety with the size of these puddles, because you mentioned that the charging energy plays a role. So
yes. Yeah.
Do you need to have very small puddles to
yes.
allow for this?
So that's So we that's a very interesting idea. I think it's a good idea. You need the charging energy of these puddles to be significant. So basically, you'll start seeing this behavior only when the temperature is below the charging energy of a single puddle. Now, that's if you work out some rough estimates, that's not so small. You can have tens of nanometers, and the charging energy might be a few Kelvin. Okay, so you can still reach that. Now, the other requirement is that if you think about a sort of inclusions of a conventional superconductor inside a metal, you want to have a tunnel barrier between the two. If the interface between the two is too transparent, then superconductivity would be killed inside these metallic inclusions. But yeah, the best way to test this would be to kind of construct an artificial strange metal using these kind of ingredients. Thank you.
In galaxy, around 20%, the T-linear regime famously extends up to very high temperature.
Yes.
How do you think about that?
Yeah. So yes. So indeed. So over here, this behavior can extend to 1,000 Kelvin. I don't believe that this mechanism operates 1,000 Kelvin. Okay. So if this picture is correct, that somehow means that the linear in T and in overdoped low temperature and the linear in T in 20% at very high temperature have a different origin. So I would have to say that somehow this and this have a different cause.
Same question. I had the same question.
You have argued kind of the general argument about Fermi liquid is that you use a phase space and that assumes sort of a constant matrix element. Yes. Then you have argued, if you have an S state which depends on energy, you can get this kind of behavior. But then, okay, you could also argue, you have a matrix element that depends on energy. And can you make some general consideration of the type you're trying to make for the denser states? To understand what is the matrix element dependence that would explain what you want to see, and then try to find what is the requirement in the interaction that gets that.
Yes. So indeed. So in the quantum critical example, the way to understand why you get a breakdown of Fermi liquid theory is due to a singularity in the effective interactions between electrons. Okay, so you have interactions that are mediated by some kind of a collective mode of the system. When that collective mode becomes soft, these interactions become singular. So really the singularity can be thought of as a singularity in the matrix element, not in the density of states. Okay, so in this sort of simple sort of perturbative analysis I've shown for Van Hove singularity, this comes in at higher order. But it does come in, and whether it actually modifies the behavior at zero temperature, it may well do that.
So that is sort of like you find some general ingredients for the singularity in the interaction, and can you I understand whether with some in ITC I'm not an ITC person, but in ITC there is antiferromagnetism, there is spin waves. You can imagine many other bosons in your system. Can you get the kind of behavior? In
some sense, So in some sense, these questions are sort of dual to each other, right? So you ask what's the low energy excitation that's causing the scattering, or what's the singularity in the scattering matrix element. So you can say if I start from some low energy excitation, like some spin fluctuation or these superconducting islands, and I integrate them out, they're low energy, so they produce some singularity in the scattering matrix element. Okay, so I think you must have some low energy excitation in the system to get a singular matrix element as well. Okay, these things are tied together. And the question is, what is that low energy fluctuation? Okay, so in LSCO, it's true, there are also low energy spin fluctuations. And the question is what's the nature of the low energy excitation? Is it these puddles? Is it spin fluctuations? Okay, in elastic electron scattering, people see low energy charge fluctuations as well. Okay, I would argue this is probably not due to spin fluctuations. In thallium cuprates, there's a very similar behavior and no low energy spin fluctuations in the overdoped regime. Okay, so another question is how to identify these puddles. Okay, so
how relevant are these ideas for the underdoped regime? And
Yeah.
especially connected to pseudo-gap, T-star,
Yes,
and all this.
yeah. So right. So indeed, in the underdoped regime, it seems like even having a sort of a Fermi liquid picture as a starting point is probably not the right starting point. We don't see even a full Fermi surface, so I don't think this is a good picture there. Again, unfortunately, I have to say, right, I'm sort of tailoring a theory for this regime. I have nothing to say about the underdoped regime, the pseudo-gap.
So, if I understand the plot correctly, at 0.2 whole doping at 200 Kelvin, there's also linear T resistivity.
Yeah.
How would you explain that? And then, if you increase the whole doping, it disappears and goes to T squared regime.
Yeah. So right. So you're asking about 20%, and what was the question again?
Well. The linear T resistivity, if I understood correctly, at higher temperatures is trivial.
Well,
it's only in the T to 0.
I mean, it depends on what you mean by trivial. People have spent a lot of time thinking about that regime, at very high temperature. There are some weird things about it that's hard to explain by the conventional mechanism. So you would say at high temperature, linear T resistivity, that can come from phonons. But then there are other questions about it. Okay, so why aren't the same phonons acting here?
Yes, and
for instance,
clearly the mechanism is not the same at 200 Kelvin as the one that you described here. Right?
Yeah. So so this is a somewhat unconventional argument, right? So for a long time, people have been arguing that this high temperature behavior sort of extends all the way down to low temperature, therefore the mechanism is the same. Now, if you look very carefully in the data, in LSCO, there is actually a subtle crossover somewhere. The slope is not exactly constant all the way down to low temperature. In other cuprates, in YBCO, for instance, there is a very similar high temperature linear T resistivity, but if you just try to extrapolate, it actually extrapolates to a negative value, which means that it can't possibly go all the way down to 0 temperature without the change of slope. Okay, so I want to argue these are different mechanisms. Okay, so the change of slope here is not enormous, so that's not completely clear.
Thank you. Let's have the last question and then continue discussion about.
Just a quick question. So you assume there's a very dilute limit for these islands?
Yes, yes, yeah.
Puddles.
Yeah.
But now, as a function of doping, would you have also an ability to predict perhaps that density getting higher or charging energy? Because you are changing the charge density.
Right. So indeed, I'm considering the limit of these islands being very, very dilute, and the reason for that is twofold. Okay, that's the thing I want to know how to solve, and because of the effect that Dirk was mentioning. If they're close enough, they'll start to lock.
Right. Well, that's actually my question. So my point is, can you predict how that locking will change the function of doping? Because that could be an experimental signature. Like that experiment in vacuo that shows the better conduction.
Yeah. So very, very roughly speaking, you would say when the distance between indeed, the picture would be what's going on here is that as we vary doping, the density of these the islands is changing, and that's why the slope of the linear T resistivity is changing. But that's also why TC and HC are changing. Okay, so so roughly speaking, when the distance between these things is of the order of a magnetic length, some fraction of a magnetic length, or a thermal length, that's where TC is, or HC.
Thank you. So let's thank Erez again.